Hi, welcome back. I am Engineer Ronald, Vincent, M. Santiago, and today we will be discussing Module 3 about unbalanced polyphase systems. And the usual causes of unbalanced conditions: first, non-transposition of transmission lines, wherein when conductors are not transposed at regular intervals, the inductance and capacitance of the conductors will not be equal. Second, single-phase transformers used in three-phase banks are not identical. Third, single-phase loads are not distributed equally among the phases. And lastly, considering the effects of faults in the system. Now, let us consider a system wherein we have this configuration, a one-line diagram. We have in the analysis of this unbalanced force, the first step is to assemble the three sequence networks. For example, in this given system, we need to develop the sequence networks. We are given here the sequence reactances as well as the terminal voltage of each component in the system. The components are the following: the generators at the left-hand side and at the right-hand side. Of course, we have the transformers both at the left-hand side and at the right-hand side, and the transmission line that connects these two part of the system. And there is a fault located at the Y-grounded delta just after the transformer. Now, we are asked to develop the sequence networks. Now, assume that the sequence reactances of all components are given in per unit values and are already converted based on the selected base MVA and likewise the base voltage. This is now the positive sequence network, wherein we consider the positive sequence reactances of all components in the system, and notice that we need to consider the voltage at both generators. We have 1.05 angle 0 degree for both generators. And for the negative sequence network, the pattern will just be the same with the positive sequence network, but we need to consider the negative sequence reactances of all components. And notice that there will be no voltages in the negative sequence network. For the zero sequence network, we need to consider the configuration of the transformers, whether it is connected Y-Y, Y-grounded, Y-grounded, Y-delta grounded, Y-delta grounded on both transformers in the system. In this system, the transformers are connected delta Y grounded and Y grounded delta. So notice that there is no zero sequence current flowing on the delta side for both transformers. So thus, the zero sequence reactance of transformer 1 will just be connected to the reference or to the ground. Likewise, for the second transformer, the zero sequence reactance of that transformer will just be connected to the ground. So this gives us the zero sequence network. Now, to create the Thevenin equivalents of this positive, negative, and zero sequence networks, we need to further analyze the system by calculating the Thevenin equivalents as seen from the fault location. In this example, the fault is at the terminal of the right machine, so the Thevenin equivalents will be as follows. So the Thevenin equivalent will just be consisting of the Thevenin voltage and the Thevenin resistance or impedance or reactance. For the positive sequence network, we now have the Thevenin voltage will be equal to 1.05 angle 0 degree. That is the voltage measured between the faulted point and the reference bus. And the Thevenin impedance will just be the impedance measured between the faulted point and the reference bus, neglecting the presence of the voltages in the system. And for the negative sequence network, so you have the negative Thevenin equivalent of that faulted system. And notice that there is no Thevenin voltage. And the same thing with the zero sequence network. Now, for system impedances, for not contributing circuit elements, so what should be the values or expected values of the sequence impedances? For non-contributing circuit elements such as transformers, cables, etc., the positive, negative, and zero sequence impedances are the same. They are equal. Second, for transmission lines, the positive sequence and negative sequence impedances are the same. Whereas for the zero sequence reactance, J sub 0, the value will be greater than the positive sequence J1 by 2 to 3.5 times. And third, for rotating machines such as generators and motors, the positive sequence reactance X1 is equal to the direct axis synchronous reactance X sub B. Then for the negative sequence reactance X2 is equal to the average of the direct axis synchronous reactance and the quadrature axis synchronous reactance. Now, if this quadrature axis synchronous reactance is not given, the value of the negative sequence reactance is just equal to the positive sequence reactance equal to the direct axis synchronous reactance. For the zero sequence reactance, X sub 0, the value of X1 less by 10 to 25%. Fourthly, for impedances of loads and feeder, these are not included in the positive and negative sequence networks. That ends our module 3, and I hope that you learned something, and I hope to see you in our next module.